Great. Thank you so much. Thanks to the organizers for the kind invitation to this very enriching workshop. I've learned so much over the last few days. I'm going to follow up a little bit on Alex's talk on the intensity mapping and try to tell you something about how in the very near future, probably the next few to 5-10 years, we might be able to do a lot with combining different large surveys in particularly intensity mapping, but out to epochs such as reionization and cosmic dawn, which are becoming accessible just now, like kind of called the final frontier. And those are where synergies really play an important role. So I'm going to tell you a little bit about how new surveys are coming up, which will help us to gain a lot of information from these exciting epochs. This is work done in collaboration with several people, Alex and several others who are either virtually or really here, as well as the COMAP, the CU Mapping Array Project collaboration, which is a carbon monoxide intensity mapping survey, whose early science we just released last year, and which I'll say something about. Okay, so this you've already heard, so I'm not going to say much about it, except to just re-emphasize that intensity mapping as this traditional to galaxy surveys, which, for example, here's a carbon monoxide survey. So this is a slightly different picture at 30 gigahertz with the VLA, for example, with a 4,500 hour survey, you're going to get these big, these bright red spots, which are not, of course, the whole story. So we know that there's a lot of stuff around it, a lot of fainter galaxies, which you would potentially access in an intensity mapping survey with a much cheaper and faster turnaround and so on. Of course, the caveat is the thing called foregrounds, the elephants in the room, which are always much bigger than the signal for many of the cases. But many of the times, it's also quite obvious that the foregrounds are very spectrally smooth, so they are different from the signal. They can be removed. And interestingly, different environments, so things like the carbon monoxide, lead to different lines. So that's what's emphasized here in this nice plot done by Guachu Sun et al. In his paper. So what is shown here is that if you have a galaxy, around it is what is known as an H2 region, which is essentially the ionized part. And there, the main species of interest is the ionized carbon, for instance, some nitrogen and so on, which really need these ionization energies. A little later, you'll find something called a photon-dominated region, or so photo-dissociation region, where C2, now astronomers' notation, 2 in front of something says it's singly ionized, 3 is doubly ionized, so you always subtract 1. And of course, a little further out, you have these colder gas, molecular gas, the most important being carbon monoxide, a very important player in star formation. And out there, really in the intergalactic space almost, and in circumgalactic space, you'll have neutral atomic hydrogen, which is what we were discussing previously. Now, the 3 main lines, which I'm going to concentrate mostly on in this talk, are, of course, the 21 centimeter, the ubiquitous spin flip transition happening at the rest wavelength of 21 centimeter, 1420 megahertz, but also the carbon monoxide, which is very interesting because in the context of intensity mapping, it has this nice ladder of states. So it has frequencies which are equispaced because you have a j into j plus 1 kind of quantum levels. So what it means is that 1, 0 has a frequency of 115 gigahertz and 2, 1 has 230 gigahertz. So since redshifts are also linearly spaced, so 1 plus z is like linear multiples, it's very nice to use carbon monoxide because the same frequency band will get you potentially emissions from 2 different redshifts at 2 different j's. So that's going to be important as we go ahead. The other structure is the ionized carbon called C plus or C2, it's variable. And essentially this one has a fine structure state, which has 2p 3 halves, 2p halves, and the wavelength of emission between them comes into the terahertz regime in the rest, but usually the gigahertz regime when we're looking at these high redshifts. And its wavelength is also 158 micron, called the sub-millimetre regime. So just like the hydrogen, we have a large number of experiments going out to detect these lines. at different redshifts. So we already heard a little bit about HIRAX. There's a bunch of others doing the hydrogen, which are either almost fully funded or even running. Similarly, for the CO and the C+, you have things like the COMAP and other experiments which go after this in different parts of the redshift space as well as the actual space. So you see some of that from this review article on intensity mapping, which came out very recently. There's also some very exotic lines you can use for intensity mapping, like doubly ionized oxygen, Lyman alpha, and things like that, some from space, etc., many of which also have been either funded or running. So just let me emphasize that, again, you heard this in the previous talk, intensity mapping is a favorite for cosmology. If you're talking big data, this is the biggest there is. You're essentially trying to access every single baryon. So until we see the dark matter directly, we have everything that we possibly could have. And you can calculate things like this. You can calculate, for instance, the co-moving volume, which is accessible to today's surveys. And that's kind of almost 1/100th of what you might be able to do in an intensity mapping survey. Just by counting information and figuring out, realizing that intensity mapping goes down to things like Jeans length, unaffected by silk damping and things like that, you potentially access about 10 to the 5 times what you could with all the surveys at your disposal right now. So that really is the strength of the big data in intensity mapping. And the main thing you want to measure from any of these intensity maps is the power spectrum. Just like the CMB, it's the 2-point correlation function of the intensity across the sky as a function of scale and as a function of redshift, because here we're doing tomography. And you may be familiar with this kind of form. Usually at large scales, you call it a clustering term, and at small scales, due to the fact that essentially intensity mapping is something discrete, there's some Poissonian short noise kind of component, usually modeled here. Now, what is interesting about the structure of the power spectrum, which will become important as we go ahead, is that it splits itself very nicely into a baryonic component, which is sitting on top of the dark matter, the CDM, for example, power spectrum, and the short noise component. So this is different from the CMB, and you can think of it as a large number of CMBs in baryons. And to do this and to quantify this, you need to model the astrophysics associated with the intensity map in a way that plays very happily with the CMB, with the kind of cosmology and the cosmological parameters. We found in a series of work, some of which Alex described, that the halo model framework, which was shown to be extremely successful for dark matter, can be adapted and reinterpreted for this purpose. Doing so takes a little bit of parametrization. And what we found is that essentially the similar kinds of arguments apply when you try to describe baryonic tracers in general, for example, hydrogen, in terms of a halo model. And you need 2 salient parts, the first being a kind of average H1 mass. It could be something else like the CO luminosity associated with a dark matter halo of mass m at redshift of Z, and the way the H1 or anything else is distributed in that halo as a function of scale. We found that essentially these 2 ingredients allow you to derive all those observables, which also was mentioned previously. And since this slide I have shown several times to this audience, I will just say a couple of sentences about it, that the contours closed much better than we ever thought they would with all the data across about 12 billion years of cosmic time. It comes from galaxies, it comes from intensity mapping, and a huge amount of the damped Lyman alpha systems between redshifts 2 to 5. And a 5-parameter framework describing the evolution of H1 and its small-scale profile clustering fits very well the ensemble of the data. What you can do with it is very interesting. We already have cosmological parameters which we're fairly confident of due to Planck and various other things. And you can change them if you want to incorporate your favorite deviation from lambda CDM. And now we can impose realistic astrophysics on top of these cosmological parameters to describe in full the neutral hydrogen power spectrum. So this is the angular version of what I showed you in the previous plot. And it tells you that this is actually a sum of these two in interesting combination. But you can do so in a realistic way by just using statistics. So shown here are some of the plots also which Alex showed, which tell you that the parameters of cosmology can be forecasted from a neutral hydrogen intensity mapping survey. But this time you can switch on and switch off, as it were, the astrophysics. So for example, there's a parameter called beta, which encapsulates the slope of the hydrogen to halo mass. It's related to things like feedback and so on in galaxies. And if you do not have it, or you do have it, you have a difference in the contour. You know exactly how much it's widening your contours. But what is very gratifying, and this is why the plots which Alex showed are completely, cosmological, is that for surveys like CHIME, SKA, and HIRAX, what we found was that big redshift coverage almost completely alleviates the effect of astrophysics. So, but this was important to quantify that how much the astrophysics and cosmology are playing with each other, and how they lead to precision in the cosmological parameters. But as we all know, precision isn't everything, and you also need to be accurate. So if you make a mistake in one of your, for example, astrophysical parameters, we looked at, with Steph Camera and others, we looked at exactly how much such a mistake, again, within a statistical framework, propagates to a bias in your cosmological parameter. So that is achieved by using what is known as a nested likelihoods framework. So the minute you have these astrophysical and cosmological together, you can do something called marginalized likelihoods and so on, nested likelihoods. And what was gratifying is that most of the parameters are within a few sigma. So you don't really have too much problems with astrophysics coming into different experiments, especially for the big ones like the CHIME and the SKA. But as we all know, on the ground, the 21 centimeter is not easy. There are a large number of things on top of the very faint cosmological signal. We saw some of these in the past talks. These are almost about a factor of 10 to the 5 times the strength of the signal. You have foregrounds from our own galaxy, and you have things like point sources and free and things like this. In addition to nuances with the experiment, you have things which you have to deal with in terms of RFI and so on. And so it is probably worthwhile to ask what we can do in the rest of the landscape of intensity mapping. So shown here are some of the extensions which are actually quite natural when you do the halo model framework for hydrogen. You can do very similar things for carbon monoxide, which I describe in some of this work, where instead of using the H1 mass, all you do is you use the CO luminosity, because that's more natural in terms of measurement. You can also do a similar thing with the C+, which is the ionized carbon. And shown here are some of the data-driven. Again, you match it to all the data we have, which is sparser, of course, in this regime. But what you get is very well in tune with what simulations predict, and also leads to quite a good signal to noise when it comes to new experiments. So this is a log scale. So you see that many new experiments are forecasted to do very well in terms of detection. In particular, the CO mapping array project, which is led out of Caltech and has a lot of us working throughout the world, has the premise that because the carbon monoxide, unlike, of course, the neutral hydrogen, it has this permanent dipole moment, so it gives us this beautiful rotational transitions. So you have this kind of band, which is what is known as the Ka band. And this band is the main band for the COMAP experiment. It's at 30 gigahertz, and it's tuned to the CO10 transition, which has a rest frequency of 115 gigahertz, coming from redshifts between 2 to 3. Now, the beauty of carbon monoxide is that the same band is going to pick up the CO21 transition coming from redshifts of 6 to 8. So just a factor of 2 greater. So because these two factors cancel each other out, you do know you have the signal inside your band. But to isolate it, you need to build another one, which COMAP will do in the future, called the Ku band, which is about a factor 2 lower in frequency. And with these two bands, if you cross-correlate, note that this band doesn't get anything from this from the low redshifts. You will actually pick up the reionization signal. So that's very interesting. As far as surveys go, it's a small one. It's about 12 square degrees. It's not too big. But this is a pathfinder, and we just recently released its early science, which is summarized in this AppJ focus issue. I should point out here that COMAP is actually the first non-21 centimeter purpose-built experiment to reach this milestone of early science. I encourage anyone who's interested to look at this issue, which describes the experiment, the pipeline, the analysis, forecasts, and prospects for reionization. The main result can be summarized in this one slide. Essentially, we have an upper limit on the clustering component of the power spectrum. This one is that power spectrum multiplied by K. That is why its shape is different. But I showed you some of these models, and interestingly, there's a tunable parameter, which is like a duty cycle, how long the halo spend being CO luminous. And that one, if it is unity, it's completely unrealistic. So it was good that it was actually ruled out by this measurement. But more realistic parameters are actually quite well, inside the scope of this upper limit. And there are several other models in the literature. You see that they span a lot. And with a 5-year survey, there is a great chance to actually put a very strong sigma on many of these models. Now, in the sub-millimeter regime, which is actually the one where the C2 and O3 originate from, as we speak, the ALMA Atacama Large Millimeter Sub-Millimeter Array is making images of galaxies all the way out to redshifts between 6 and 9 in regimes where we still do not have our first 21 centimeter. So it's worthwhile to ask, with these kind of lines, especially C2 and this O3, which is doubly ionized carbon, what could be our prospects to do intensity mapping? Pathfinders are already on their way. They're going to fly in the next 1 year to 2 year time scale. The first ones, the reason why we use these two, especially these two lines, is because they're the brightest ones in their regime. So as you see a typical galaxy spectrum, the O3 and C2 are very bright. They don't suffer from many of the disadvantages associated with observing from the ground. In fact, there's a balloon which is going to observe O3 over the redshift range of 400 to 500 gigahertz. It's called XCLAIM. And there's also the Fred Young sub-millimeter telescope called FEAST at the Cerro Chajnantor, observing the C2 or the C+, the similar kind of gigahertz regime. So this is the regime where the sub-millimeter is happening. And of course, we want to bring them together with other things so that we understand and have a comprehensive picture of the galaxy evolution, CO, H1, C2, etc. So to do this, the first thing we need to ask ourselves is about cross correlations, about synergies in general. And as we probably all know, if you have a survey and you do kind of autocorrelation, then essentially you will be left with noise which you really do not want. So you're going to have this noise component. But unless something is conspiring against you, if you do a cross correlation with a completely different survey, chances are these noise terms will cancel out. So you'll be left with exactly what you want, and foregrounds and other things become less of an issue or an almost non-issue. This was something recognized since almost 20 years ago, and they had these things about cross-correlating 21 centimeter with galaxies. The trouble is that if the galaxy surveys are too small, then especially at reionization regimes, you get information loss in areas which have what is known as the foreground wedge and so on. So there's practical difficulties with it. But this is very well mitigated by using intensity mapping with a sub-millimeter kind of survey, a survey which is covering a few hundred square degrees or more. And so this was only a theoretical dream when it was written, but in the next few years, and definitely 2-3 years, it's going to soon become a reality. The way this works is as follows. If you have all these intensity maps, this is a review article which kind of shows you where they all overlap with surveys that we already know of. So COMAP, for instance, and various other ones with the large galaxy surveys. And if you do the 21 centimeter large galaxy surveys, this is something we did again with Alex and Adam Amara in 2020. We find that if you take CHIME and DESI, which has been talked about a lot, of course, here, you can do constraints on cosmology and astrophysics. Ignore the y-axis here because that is a function of various other things like foregrounds and so on. But essentially what this plot is telling you is that astrophysics is essentially not important. It's just the same as doing the tomography. If you do cross correlations with the tomography, you really do as well as you would had astrophysics not been present or had all those parameters been fixed to their mean value. What is more, you can actually do better on the astrophysical parameters themselves by factors of 2 or more, even 3, with this cross correlation. So cross correlation with a galaxy survey is actually helping you refine your astrophysical forecast. They improve from the present trials. And very recently, there have been insights which allow you to take this further out, almost to mid stages of reionization. People have found with studies of the WIM, which is around galaxies and so on, that the total amount of H1 in the IGM, in the universe, could be very well described by what we would get just by extending the halo model framework out to redshift 7 in a regime where it was not matched to the data. That's very exciting because, of course, it's the total power only. It allows us to do very interesting cross correlations. So for instance, if you do cross correlations of the sub-millimetre regime, so I told you about the FEAST experiment going after C2, and a pathfinder to the square kilometre array, the Murchison wide field array, you can go all the way up to redshift 7, and you can find signal to noise of a few to a few 10. Sometimes for extremely optimistic carbon to signal measurements or signal forecasts, it can go a few hundreds. The lines in this of the signal represent the latest we have from ALMA on the C2 luminosity function, which has now been mapped all the way up to redshift of 7. So it's very promising. And note that in this picture, I don't put foregrounds or instrument noise because it's a cross correlation. So people have already started trying to do this with AGN, and there is also interest in doing AGN C2 because, of course, the first AGN at redshift 6 was indeed discovered in C2 in sub-millimeters. So there's a lot of hope to do AGN feedback, and here people use the model which I showed of the C+ to derive very strong signal to noise of quasars and C2. You can do similar things with carbon monoxide and quasars, and people did that again in some of these papers. So I think to summarize, the future definitely lies in synergy. So there are going to be all these different intensity maps covering vast swaths of the universe across from today all the way probably until the edge of reionization. Combining them with things like the James Webb Space Telescope and studies of AGN, which are probed by, for example, the gravitational wave mergers, their mergers and their resultant gravitational wave emission. We didn't get to talk about that, but that's also very exciting. Would probably provide us the most interesting picture of the universe. Let me just summarize by telling you that line intensity mapping is an emerging technique, probably going to become more and more timely in the next few years. It bridges a gap between deep and wide spectroscopic surveys. And the thing about line intensity mapping is that it's a kind of map of baryons. So it has this astrophysical systematic, and it can be handled via this data-driven halo model framework, exploring the impact of astrophysics on both precision and accuracy of cosmological forecasts over large amounts of cosmic time. And not only that, cross-correlation synergies become very important, especially in the sub-millimeter regime, which is getting a lot of interest right now. Systematics and foregrounds can be effectively reduced for new 21 centimeter surveys out to the epoch of reionization using the power of the sub-millimeter. Increasing the signal to noise is definitely one of the results of this, but also they can be cross-correlated with each other and reach factors of 10 or 10 sigma or more when you do this kind of cross-correlation. So I think it's fair to say that combining this learning with the multi-messenger information that's soon to come with LISA and also pulsar timing array would help us secure our most comprehensive picture out to cosmic dawn. Thanks a lot. I'll stop here.
Time for questions. for this great talk. And I think we had some of this conversation before, but I wanted to understand this a bit better. So for things like COMAP, you're talking about surveys, you really need to resolve halos much smaller than we typically resolve in these kinds n-body simulations these days. And you need really large volumes. And so this seems to be the place where we are not yet. And I don't know if you have thought about it, where will we be and what are the alternatives if we can't do n-body simulations of those resolutions and volumes?
Yeah, so we do not, none of these are n-body. Some of them are hydro, which are very, very strongly focused on a galaxy, and then they just do some kind of zoom in, zoom out so that they get more. But most of these are semi-analytic, and mine, of course, is data-driven. It's not a simulation, it's empirical and completely from the data. But I think essentially we do either of the two. We either do a large-scale data-driven CO framework, which is well described by a double power law, and there's a lot of CO data coming in from new experiments which are informing that model. Or we do a detailed hydro, which there's something called Yang et al., which is there, probably it's not in this, but in another one, where they do a full hydro with all kinds of things because they need chemistry and things like that, and then they just propagate. So I think the approach of the 21 centimeters is not exactly what you need to do for CO. You need to do more. I think the best way really is the data-driven way, because we have a lot of data from individual sources, and when we exploited them here in COMAP, we found that the models which were in 2018 were refined several times because of the information from the new data, and they fitted things quite well. So that is how I think it should go.
Just follow up a little.
Yes.
So you're saying like we can completely bypass need of a big in-body simulation at the resolution?
We should probably, unless you're doing a full chemistry and so on, don't do the in-between. Either do a broad scale thing or a complete chemistry. And in fact, complete chemistry is needed for, instead of CO, even C2, because people found metallicity relationships and they want to understand that. So that is one of the reasons for that. Yeah.
So just following up on this, so if you bypass simulations, what do you do about covariances?
At the present time, I think you essentially do the covariances from whatever hydro they have. So the hydro which they have like adaptive meshes and so on. So they take covariances from the smaller, smaller volumes, and they just scale them up with the help of some semi-analytic scalings. So SAM's kind of models.
Maybe I'm missing something, but what about the covariances for correlation functions?
We don't have those yet, no. It's only at the level of power spectra now, and there are no correlation functions.
Power spectra, covariances for power spectra then?
No, we actually do not, we don't really have, it's just an upper limit at the moment. So I think most of it will be handled via SAMs and, some sort of hydro on top of dark matter thing. So they still,
Yeah. When you say that foregrounds will not be a big challenge when you cross correlate, so is it because you're measuring in the different wavelengths?
it's not, it's because you're measuring with different instruments and of course different wavelengths, but you're measuring different surveys. So 21 centimeter will have its own challenges and CO will have its own challenges. You combine the two, then most of the time things won't conspire so that the instrument and foreground will be the same for both. Definitely it's not the case for CO and 21 centimeter.
Okay, thanks.
That's why.
One last question.
Yeah, so about this, you showed that if you use tomography, then a lot of the astrophysical systematics of the parameters can be better constrained.
Yes.
So how much freedom are you allowing for any redshift dependence to your model parameters for the moment? Whatever
the data allows at the moment. Some of these are indeed redshift parameters. So, I mean, if you can see this, this is a redshift evolutionary parameter. And we found, in fact, we allowed other things to vary and the MCMC stubbornly refused to incorporate redshift dependence. So it actually preferred Occam's razor preferred a much simpler model. So whatever the data allows so far is allowed.
So you keep these redshift dependencies also?
Oh, yes.
Yeah.
Indeed. All of the redshift dependence is across redshift 0 to 5. Yeah. There was already very good. Yeah. It's much more than we ever thought it would be. Yeah. Even the new ones are fitting out of the box. So yeah, so just yeah, so that's quite interesting. It's very robust. Yeah, we didn't expect it so much.
Let's thank Hamsa again.